Good evening, all of you. Is my voice clear? So let us begin our today's session. Any queries for anybody or the previous class? There we have discussed about how to prove that a given set is a group with regard to a binary operation given on that set. To anyone? Any questions, any doubts to anyone? All right. Then one property we have to consider is, we know the property of law of integral exponents. Can you recollect these properties of school level? Right? So this kind of properties will hold good in a group. It means if you take two elements in a group, then we can say that AB whole power m is equal to A power m, B power m. A power m into A power n equal to A power m plus n, etc. This kind of properties hold good in a group, which we call it as the law of integral exponents. You please take a note of that point. Now formally, after defining a group, some kind of definitions will come observing the properties of group. If you want to prove that a set is a group, we need to verify four properties: closure, associative, identity, and inverse. If the first two properties are satisfied, closure and associative, that type of set we call it as semi-group. So what it means? I have a set, I am given an operation on that set. The operation satisfies only two properties on that set. Then we call that set as semi-group. If three properties are satisfied, we call it as monoid. If all the four properties are satisfied, we call it as a group. And one more property is there, the fifth property. If five properties are satisfied, then we call it as an abelian group. Okay? And there is one property, we call it as cancellation loss. Suppose I have taken two elements in a set. So if I say that C plus A is equal to C plus B, then we can, after cancelling C, A is equal to B. Agree? For numbers, we do like this. Yes or no? Similarly, if you take any operation, say circle, so C circle, is equal to B circle C, cancelling we see, we say that A is equal to B. So this type of properties, we call them as cancellation laws. So here there are two cancellation laws. If the element what you are cancelling is on the left hand side of the operation, we call it as left cancellation law. If the element is on the right hand side of the operation, we call it as right cancellation law. So there are two cancellation laws, left cancellation law and right cancellation law. You please take a note of them. So cancellation laws hold good in a group. So for the elements in any group, we can apply the cancellation laws. We can say one more thing, that there are semi-groups where cancellation law gets satisfied, but it is not a group. For example, we have done with the natural number system n comma plus. So you take the natural numbers n and the operation plus. So there you can easily verify that if we know that n comma plus is a semi-group because it has only two properties, closure, associative. Identity property is not there because 0 is not an element in the natural numbers. We already checked that part while discussing about the group. So cancellation laws will hold in a semi-group, but it need not be a group always. I will give one more example, that suppose you have taken matrices. There also we can talk about the cancellation laws. So one small example I want to give is or you are getting any disturbance in the voice. Here now, fine. You can't hear my voice. Is everyone the same problem? Right. Now you consider the 2 by 2 matrices. We know that it is a semi-group. Now, if you observe the thing that we can say AB is equal to AC. Can we multiply the matrices? What is AB and what is AC? Is it zero matrix or something different? You agree or not? Right. So we can say that it is a zero matrix, correct? Now, if you apply the technique of cancellation law, which gives that B is equal to C. Is it correct here? Is B is equal to C in this problem? So, after these examples, we can understand 2 points that cancellation laws not hold always in a semi-group. The second point is there exist semi-groups with cancellation laws, but not groups. So you can find some semi-groups where cancellation laws will hold, but those semi-groups are not groups. And whenever you have a semi-group, there is no guarantee that always cancellation laws will hold in that semi-group. This is one example. This is one example for the discussion. Okay. So why I am going to prove these things? So there is one good theorem which is also given in the previous year question papers that we discuss right now. Shall I continue? All right. Usually, so the second point is there are some semi-groups, even though cancellation laws hold in that semi-group, they won't become groups. Example, n comma plus. Natural numbers with operation plus. Please understand the results what I am telling right now are useful while doing some kind of problems in the exam, right? So we are not going to do any special kind of problems based on these results, because every result what I am giving here has a theoretical proof. So we are not going to the theory. Our concentration is with regard to the exam point of view, how much we are going to understand and concentrate on previous year question papers. So one thing is, if you take a group, say G comma dot is a group, then AB whole inverse equal to B inverse A inverse. So whenever you take two elements in a group, then inverse of AB equal to B inverse into A inverse. You take a note of this point. Another point is, usually while saying that G is a group, by default we have to understand that the operation is dot, multiplication. So usually the operation on group notation, G comma dot is a group, S comma dot is a group, etc., etc. And the other result is, So this is one good result, that whenever you take a group G comma dot, you consider two equations, Ax equal to B, Ya equal to B. So whenever you consider an equation of this form, they will have unique solution within the set. It means that in place of X, we can find a value in the group so that equation gets satisfied. In place of Y, you can find a unique value in the group so that the equation gets satisfied. Okay? Now, the result is very simple. If you consider the first equation, Ax equal to B, you simply multiply on both sides with A inverse. So applying associative law, it is the value so the value of X is nothing but A inverse B, which satisfies the first equation. Similarly, if you multiply both sides with A inverse on the right hand side, you will get Y is equal to B A inverse. This is the solution for the second. And I will say that the solution is unique because whenever you take two solutions, they will become equal. So since x1 is a solution, you can write it as ax1 equal to b. Since x2 is a solution, you can write it as ax2 equal to b. So for a value b, you have two representations. You can write that ax1 equal to ax2. So by applying cancellation law, you will say x1 is equal to x2. So whenever you say that there are two solutions for an equation, they are becoming equal. So the solution is always unique. So this condition is useful because whenever you want to prove that a set is a group, apart from proving the four properties, we can prove these two properties. So I have taken this type of equations in that set and they have unique solution, hence it will become a group. So this type of condition we use to prove that a semi-group will become a group. You please take a note of that. Apart from verifying the four properties, you can verify this condition to show that a given set becomes a group. If you have noted this, then I take the next one. After noting, you please tell. I have given some problems on addition modulo and multiplication modulo as an assignment for you. Have you done it on the previous class? So did you get any confusion while solving that problem? Any one of you? How to draw the composition table with the operation given? All right, I think you feel comfortable in solving that problem. So the next question is, a finite semigroup satisfying cancellation loss is a group. A finite semigroup satisfying cancellation loss is a group. You take a note of that. Now, so you have to consider a finite semigroup here. So let us take a set, say G is equal to A1, A2, so on AN is a finite semigroup. With cancellation loss. So what is our claim here? We have to prove that it is a group. We know that group means four properties: closure, associative, identity, inverse. Since we have taken a finite set which is a semi-group, it has two properties: closure and associative. So how many properties are there for myself to prove it is a group? Tell me. How many properties I have to prove to show that it is a group? Actually, four properties: closure, associative, identity, inverse. So here, two properties are already given in the problem because it is a semi-group. So I have to prove the remaining two, isn't it? Identity and inverse. Right. So apart from proving that the properties identity and inverse will hold in that set, I prove that based on the previous discussion what we made, the equations Ax equal to B and Ya equal to B have unique solution. So as per the previous discussion concerned, I will show that whenever I take an equation of the form Ax equal to B, I will get a solution in G. Whenever I take Ya is equal to B form, then I will get a solution in G. So based on the previous discussion, it will become a group. So I am not proving directly the identity law and inverse law because I don't know what are the elements in that set and I don't know what is the operation on that set. These things are not known to me. If the operation and elements are given, then I can verify what is the value for the identity element, what is the value for the inverse element. Here these things I don't know. That's why based on the previous result, I will prove this situation will exist in the set G. Okay? Is it clear for you? Right. So this is a finite set, please understand. Among all these elements, you pick up one value, say A. Now, let us multiply all these elements with A. Since you are taking the elements of G itself, By closure law, all the values belong to G. You accept or not? Now, I will say one more thing, that all these values are distinct. Because if you say that among these values, if any two values are equal, say, for example, A3 is equal to A10, let us say. Since it has cancellation loss, you can apply the value A, you will get A3 is equal to A10. Is it correct? Wrong. Because I have taken these values as distinct. A1, A2, so on, AN are different values and is a finite set. So these values are totally distinct values. If you have a small doubt, let us take a small example. Say, take the set 1, -1, I, minus I. This is my actual set G, right? Among all these values, you tell me one value here. -1. So with the elements -1, you multiply all these values. So what I am doing, -1 into G I am doing. Just like if I take an element, I am multiplying all the elements of G with that element. So it is nothing but -1 into 1, -1 into -1, -1 into I, -1 into minus I. You accept or not? So all these values are distinct. You agree? No value is repeated. And all these values belong to the actual set G, right? So if you observe that, the interesting thing is these two sets are equal. That means what are the elements in this set are same, the elements in this set. Maybe the order is different. Here first element is 1, second element is 1 here. Here I is the third element, here I is the fourth element. So element position may be different, but sets are equal. Agree? So that I am going to mention here. So since it is a finite set, these two values are equal. There is no other possibility here. Since G is finite, the set of values A1, A2, so on, AN is equal to the set of values A1, A2, so on, AN. The set and the resultant set both must be equal in some order. So if I take any element here, so it must be equal to one of these values because these two sets are equal. So if I take any value here, it must be equal to one of these values. Agree or not? Therefore, there exists an element AI belongs to G such that AI is equal to B. Now you can check that this is of the form AX is equal to B. So what is X value here? AI. So it means that whenever I consider an equation AX equal to B with the elements of G, then the solution of that equation also lie in the same set. So similarly, apart from taking the products from the left hand side, you take the products on the right hand side. So if you have written A1 into A, A2 into A, A3 into A, so on, AN into A. So by considering right hand side products, you can say that the equation YA is equal to B has a solution. So as per the previous result concerned, given set becomes a group. So what is the overall idea for this problem? A finite semi-group, if you take, having cancellation loss, it will become a group. So to say like that, I am proving if you take a set with given hypothesis, in order to prove the properties of identity and inverse, I am proving that whenever you take an equation of the form Ax equal to B and Ya is equal to B, they have unique solution in the set. Therefore, by the previous result concerned, it is nothing but a group. That is the overall view. It is a small theorem given in the previous year papers. That is why I have chosen this for discussion. Okay? Are you comfortable in getting the idea? Please tell. Now let us do one more problem. It is also given in the previous papers. Because in group theory or abstract algebra you call, majority of the questions are repeated ones and examples. You have very less number of material to prepare. If G is a group such that AB whole power m equal to A power m, B power m for three consecutive integers for all AB belongs to G, then G is abelian. You please take a note of this problem, then we discuss with the approach. After noting, please tell. So if you look at the hypothesis of the problem, it is already given that G is a group with one additional property that whenever you take any two elements in the group, then this property will hold for three consecutive integers. It means that AB whole power m equal to A power m, B power m, AB whole power m plus 1 equal to A power m plus 1, B power m plus 1, AB whole power m plus 2 equal to A power m plus 2 into B power m plus 2. This is the actual meaning. If you take any two elements in the group and this condition will hold for them, then the group will become abelian group. So what is meant by abelian group? It is having commutative property, nothing but xy is equal to yx. So whenever you take any two elements in the group, they will exhibit this property, just like 2 into 3 is equal to 3 into 2. Please understand that for numbers it is okay, for matrices it is not okay. The properties what you are discussing in group theory are applicable for numbers, functions, polynomials, matrices, everything. Don't confine your understanding with regard to numbers only. It is applicable for everywhere whenever you have a set and an operation. Okay? So we have to prove that this property will hold. So we can say that G is abelian. So what is our prime motto here? I have to prove AB is equal to BA. And this is my hypothesis given in the problem. So first of all, let us consider this. AB whole power m plus 2. We can write it as AB whole power m plus 1 into AB. So my intention here is I want to bring the relation AB is equal to BA using these three conditions and cancellation laws, because in every group cancellation laws will hold. That is my main objective for taking like this. So again, this can be written as so I have applied these two. I have applied them. Again, this can be written as A power m plus 1 power m plus 1 into B is equal to A into A power m, B power m into B, A, B. Any doubts for anybody here? Please tell. Now, if you apply the left cancellation law, the leftmost element is A, it gets cancelled. If you apply right cancellation law, the rightmost element is B, it gets cancelled. So you got this thing. So this is nothing but AB whole power m plus 1 equal to, this is AB whole power m into BA. Again, this part can be written as AB whole power m into AB. Again, applying the cancellation law, AB whole power m gets cancelled, we will get this relation. Therefore, AB is equal to BA is satisfied, hence G is an abelian group. You please take a note of this. It is just like logically arranging the values to get the required solution. After noting, please tell. If you have any confusion, you can ask. So now we are going to define some definitions. Order of a group, order of an element in a group. Now we discuss about the properties and definitions based on this concept. It is very simple that if we have taken a group G, then the order is nothing but the cardinality of the set. So total how many elements are there in that set. So we denote with the symbol order of G. or you can write it as G with the symbol modulus. It indicates order of the group. You can write like this or you can write like this. And what is order of an element? So it is nothing but whenever you take an element in the group, there exists a least positive integer n such that a power n is equal to identity. This is the most important definition. Majority of the questions and problems and theorems are also based on this concept while going to the higher classes in our class sessions. So order of an element is nothing but a least positive integer n such that a power n is equal to e. Okay, so if you want a small example, let us take that. So take the value 1 minus 1 I minus I. This is the group and the operation is dot. Now 1 is identity, we know that. So apart from this, you have 3 elements in this set. So you pick up one element among them, say minus 1. Since the operation is multiplication here, you raise the powers. Minus 1 whole power 1, minus 1 whole square, and so on. So while raising the powers, you should get the identity element. So here it is nothing but minus 1, here it is nothing but 1. So the identity element has come for the power 2. Therefore, order of minus 1 is equal to 2. Did you get it? Now, you take the other value I. So you have I power 1 is equal to I power 2 minus 1, I power 3 minus I power 4, 1. Agree? So if you observe that for the power 4, you get the identity element. So order of I is nothing but 4. So here one interesting thing is it is the least positive integer. So before 4, if you consider any power, you are not getting the identity. Did you get the point here? The power is the least one, so that if you take any power less than that number, you cannot get identity value. That is the concept of the order of an element. And one interesting thing you can observe is, while considering the powers, the resultant values are nothing but the elements in the group. If you say I is an element, say A, I have calculated first power, second power, third power, fourth power has become identity. So all these values are nothing but belonging to G. Can you observe here? So whenever you take an element, while raising the powers, all these values will belong to group, because by closure law it is possible, because you are performing the operation on the element. And one more thing is, the power is the smallest one, so that if you take any power less than this, you cannot get identity. That is why order we call it as a least positive integer n such that a power n is equal to e. So we are considering the group by means of the operation multiplication here. Please understand, order means you are applying the operation on the group repeatedly on one element till you get the identity. So how many times you are applying the operation, that power we are calling it as the order. For example, if you take our previous class problems, I have given two things for you. One problem I have given that is Z5 comma plus 5. Can you remember the problem? I have given to calculate a composition table and verify it is a group to everyone. Say, so if you that set, Z5 is nothing but 0, 1, 2, 3, 4 and the operation is plus 5. Here 0 is identity. So you exclude this value, consider the other parts. Let me say I have taken 2. Now, if we consider that 2 plus 2, see here I am applying the operation repeatedly on one value. Please understand. Here we are not calculating the powers of 2. Here we are adding 2 because the operation is addition here. So this is nothing but 4. If you do 2 plus 2 plus 2, it is nothing but 1. If you do like this, it is 3. Do you accept? As per the addition modulo m, that we will get the results. Yes or no? So here 0 has come by applying the operation for 2 on how many times? 5 times. So order of 2 is nothing but 5. And you can do the other thing. As we have constructed the composition table, can you tell what is the inverse of 2 in the table? Three. Now let us calculate the order of 3 there. This is 1. This is 4. This is 2. This is 0. So here order of 3 is nothing but 5. So you can say 2 and 3 are inverses to each other. Inverse of 2 is 3, inverse of 3 is 2, and they are having the same order. Did you observe that? So one more thing I can say. Total how many elements are there in that set? 5. So order of the group is 5. If you calculate any element order, it will not exceed the group order. So order of an element will not exceed the group order. It is true for every group. So it is a theorem. It has a theoretical proof that I am skipping because it is not required for you. So whenever you take an element in a group, if you calculate its order will not cross the total number of elements in that group. Okay? If you have taken an infinite group, there is a different issue because you will get infinite order that you cannot literally say this is the element of, this is the order of the element. So we are talking about the finite groups. So order is also a finite one. In general, we talk of that. So you can do the part with multiplication. I have given one more problem, that Z7 into 7, where Z7 contains the elements 1, 2, 3, 4, 5, 6. You can apply the same technique for the elements in Z7. So you take each element in the set, calculate the order. So you are applying the operation multiplication modulo 7 repeatedly on each and every element till you get the identity. Okay? That I left as an exercise for you, that you can do it on your own very easily. And one interesting thing is, whenever you take identity element has always order 1, because 0 power 1 equal to 0. So every group, whatever the group you consider, the identity element has order 1, that is fixed. Now let us do one more thing. One good observation we can do. So earlier we have taken that the group G is equal to 1 minus 1 I minus I. And we have calculated order of I also. This is equal to 4 we have mentioned. Now after 4, again you calculate the powers of I power 5, I power 6, I power 7, I power 8. You go on calculating and tell me at what power you get again identity. Please tell that. You calculate and tell. You raise the powers of I after 4. I power 5, I power 6, I power 7, I power 8, I power 9, and so on. I power 8. Is everyone agree for that? So here the observation is, as we know, I power 8 is equal to identity. The order what you got will divide this power. Did you observe that? Again, you keep on raising the powers. I power 9, I power 10, I power 11, I power 12, I power 13, and so on. Tell me at what path you will get the identity. You will get I power 12 is equal to 1. I power 16 is also 1. So you can say that this order, the order of the element, is dividing the powers, and so on. You get the logic? So this thing we can frame it theoretically. How? If G comma dot is a group and A is an element in G with order n, then A power m is equal to identity if and only if n divides m. So while raising the powers, if you get identity, then order must divide that power. This is the thing you got. So which we are going to prove theoretically. If you are ready, then we will prove it. Right. Now, it is an implied and implied by situation. So you have to prove two conditions. Assuming this, you have to prove this part. Again, assuming this, you have to prove this part. So let us assume that n divides m. So what is our claim? A power m is equal to identity. Since n divides m, from this part you can say that m is equal to some number n into, because n divides m means m is a multiple of n. So you can write m is equal to n into some number. Now you consider the value a power m. So it is nothing but a power n cube. I have given the law of integral exponents will hold in a group. X power m into x power n is equal to x power mn, etc., etc. So applying this condition, you can write it as a power n whole power q. Since a has order n, it is nothing but identity whole power q. It is nothing but identity. Please check that. How it is proved. Any questions you can ask? Right. Now, if you assume this part, we have to prove that n divides m. In other words, you have to show that m is equal to a multiple of n. So please understand that basically the values n, m, etc., etc., all these are nothing but numbers. The integers we are talking about. So whenever you take integers, they will satisfy division algorithm. I think you know what is meant by division algorithm? Yes or no? But you know that I will give you. See, whenever you take two numbers, let me say I have taken a number 5, you take another number. Whenever you have two numbers, we can do like this. So you can write 13 is equal to 5 into 2 plus 3. Have you seen this expression earlier? So this we call it as dividend is equal to divisor into quotient plus remainder. Accepted? That is nothing but division algorithm. So whenever you are dividing with a number, here this part we call it as the remainder. So what is the possibility for remainder there? Let me say here I am dividing with 5. I am dividing any number with 5. So what is the possibility for remainder there? What is the maximum possibility for R there? 4. That means you can get 0 as remainder, 1 as remainder, 2, 3, at most 4. You cannot get 5 as remainder, isn't it? So here also we apply the same technique. So since m is a big number, n is a small number, we can write it as m is equal to n into q plus r, where q is quotient, r is remainder, and the possibility for r is 0 less than or equal to r less than n, because we are dividing with n. So here you have got two things. R may be 0, r is not equal to 0, so that r is less than n. Because I got two numbers here, one number is m, one number is n. I am dividing m with n. So I got a remainder r. So the remainder, as per the discussion consent, it may be 0 or it is bigger than 0 or smaller than n. It has two possibilities. Agree? So what happens if r is 0, then from this expression m is equal to n cube. So we can say that n divides m completed, because m is a multiple of n. So in this case the result is clear. Now you have to check that whether there is a possibility that remainder may be something else apart from 0. So I have to show that If this case exists, I will get a contradiction. In other words, this case is practically not possible. That is actually what I want to say. The remainder is 0 perfectly. You cannot get a non-zero remainder in this case. How? We can discuss right now. If you consider this case, if R is non-zero and 0 less than R less than n, so we know that a power m is equal to e, because we have assumed this thing. From this, a power nq plus r is equal to e. This implies a power nq into a power r is equal to e. You please observe that. So after applying division algorithm, you have two possibilities for R. The remainder may be 0. The remainder may be non-zero. Here I am saying that having remainder a non-zero number is practically not correct. That is I am saying. Why? Because you know that a power m is equal to e. You got a value for m. Substitute here. You simplify this. Since e is identity, if you multiply any element with identity, you will get the same element. So a power r is equal to e. So at this point, we have to understand that r is a number. I am raising the powers of a up to the number r. I get identity. And I have one more thing, that r is less than n. So this is a contradiction, because since you have taken that order of the element is n, it means that n is the least positive integer to get the value a power n is equal to identity, because you have practically taken so many examples. So before n, you cannot get identity. It is practically not correct. So here what happened? A power r is equal to e, and r is a number which is less than n. The order of the element, it is practically not correct. So this is a contradiction. Okay? Did you get the meaning? How the contradiction has come? Right. So therefore, the only possibility is r equal to 0. So if you put r is equal to 0, m is equal to nq, hence n divides m. This is the proof of the theorem. This theorem is given earlier in UPSC exams. So with regard to examination point of view, I am proving the theorems. Please understand. Other theorems I am not discussing. I am just giving the statements for you for your consideration. Because if I start proving theorems, you will get a lot of boredom, because it involves a lot of logic and thinking. These are not our regular formula based problems. All these are based on fundamental concepts and definitions. So one should be good at logic in understanding these things. Is it clear to all? Right? Then if you have noted this, I will take one more problem. Okay. So this is a problem given in UPSC. Please take a note of this. After noting, please tell. Now, if you understand the problem, I am given a group G comma dot. In this, I have taken two elements where one element has order 5. Immediately, what we can think about A power 5 is equal to identity because order of A is 5. Can we say anything more about the order? We can say that order of A inverse is also 5. Because as we know that A and its inverse both will have the same order. We have done a problem. Under Z5 plus 5, we discussed that 2 is a number whose order is 5. 3 is another number whose order is 5. Both are inverses to each other. Can you check the result? Right. So after reading this step, we can say like this. And one more thing, B is not equal to identity. So if you write the group contains identity element A, B and other elements. These two are different. Identity is different, B is different. And one more property is given that if you multiply these three values, the result is B square. So we have to calculate order of B. That is the problem. Clear now? It is also a previous year question. So here we need to understand that since we are going to calculate the order of the element, as we know, if you take an element, raise the powers, you should get identity at certain power. And the power must be the smallest one. That you need to ensure that this power is the smallest one so that I will get the identity value. So it means that if I keep on raising the powers of B at a certain power, I should get identity. And this power must be the smallest one that I have to prove. So how to do? That is the question. So while raising the powers of B, I will consider only the even powers because there is a relation given with even powers. AB A inverse is equal to B square. Now I am going to do the part. Please observe. So first of all, I am going to consider AB A inverse whole square. So this is nothing but AB A inverse into AB A inverse. A inverse into A is nothing but identity. So this is nothing but AB identity B A inverse. Again, identity into anything is nothing but the same value will come. So it is A B square A inverse. So using this part here, A into AB A inverse into A inverse. So in place of B square, I have substituted the respective value. So this is nothing but A power 2 B A power minus 2. Did you observe? Say, please take a note of that. Any questions with regard to the logic applied here to anyone? right? Now I am taking the next power, I am taking like this. I am taking the power whole power 4. So this is nothing but AB inverse whole square into AB inverse whole square. So just now we have calculated its value. So this is nothing but a power 2 b a power minus 2 dot a power 2 b a power minus 2. Again, this part is nothing but identity. You can write it as a power 2 b identity b a power minus 2. So again, a power 2 b square a power minus 2. So b square is nothing but a inverse a power minus 2. So this is a cube b a power minus 3. You please check on that. So I will say that if you calculate a inverse whole power 8 doing a inverse whole power 4 into a inverse whole power 4, you will get the value as a power 4 b a power minus 4. You please check that. You do it on paper on your way, just like this. And if you consider this part, a inverse whole power 16, you will get that a power 5 b a power minus 5. You please do it these two things on paper from your side and give your confirmation. After finishing that, I will wait. I think this kind of pattern you are following there. You please check these results have come for you. Is everyone finished them? After finishing, you tell. Shall I continue? All right. Thank you. Now see, we have already known that a power 5 is equal to identity and a inverse whole power 5 is also identity because both have same order. 5 is the order. So at this part, this is nothing but identity b identity nothing but b. So this part is nothing but b square. So if you substitute here, b square whole power 16 is equal to b implies b power 32 is equal to b. Cancelling b, you can say that b power 31 is equal to identity. Agree? At this position, I have substituted the value of b square, which is given in the problem. Now here, if you observe that I have raised the powers of b, at this power I got identity. So 31 is the number at which I get identity value for b. But I don't know whether 31 is the smallest power or not. Because if there any smallest power less than 31, for that also can I get identity for the element b? I don't know. That I have to check. Because straight away I cannot confirm that 31 is order of the element b. Do you agree? So for this, just now we have proved a theorem that if order of an element is n, then a power m is equal to identity if and only if n divides m. So it means that order of an element always divides the power at which you got the identity. So from this perspective, we can say that order of B divides 31. Any confusion in applying this result? Say. So if you observe that, what are the divisors of 31? Since 31 is a prime number, 1 and 31 itself are the divisors. Therefore, the only divisors are 1 and 31 itself. So there are two possibilities. Order of B may be 1 or order of B may be 31. So there are only two possibilities for B. Accepted? So here what happens, if you read the problem statement again, it is given that B is not equal to identity. As I mentioned, if you take any group, always identity element has order 1. So E has order 1. Since these two are different, B cannot have order 1. So the first case has no possibility to exist. So this is the only possibility. So order of B is equal to 31. Fine. So in exam, we write that since B is not equal to identity, order of B cannot be 1. So the only possibility is order of B is equal to 31 that we have to mention. That's it. So this is the solution of the problem. So whenever this type of questions are given to you, the minimum weightage is 15 marks in the exam, 1-5. So here you need to understand one thing, that while solving the problem, apart from the logic, I have used three things. One, the previous theorem. Two, the order definition. There is one more result, order of A is equal to order of A inverse. So consolidating the three, I have proved this problem. Did you get that? If the three things are not known to me, I cannot solve this problem straight away. Even the solution is given clear to you, you cannot understand what it is actually. So the underlined idea in abstract algebra is, there is no need to learn the complete proof of the theorem. So for every class, before going to start the class session, you have to prepare for the theorem statements. So what is the previous class? What are the results we have learned apart from the proofs and problems? So these are the results. So you have to make a note of these results. Only the statements you need to consider. You have to by heart those statements as well as definitions. If you are not good enough in understanding these fundamentals, then you cannot follow the further sessions. They will be more difficult. Because in every class, I will take a new concept. I will give the illustration on that. While proving certain kind of theorems and problems, I will make use of the previous results. That is the thing. Okay? Did you get that now? That's it. So let us wind up our session here. Thanks for your good listening, and we will meet on Monday. If any doubts you have, you can ask to anyone. And can you comment on, is it good for you in learning abstract algebra? Are you comfortable in getting the logic? Or feeling difficult to learn? I have already told that the best part of abstract algebra with regard to UPSC is there are more number of repetition of questions. There is no huge material. The material is very small. One small book is there. In that, we are learning selectively some concepts, that's all. Nothing else. So the number of problems and concepts are limited here compared to other units of the syllabus. That's it. Thank you.